ladies and gentlemen, class recording has started. So, real quick, just as a reminder of where we're going here for the next couple of days. Yesterday, we started off with momentum, and we talked about what momentum was, did a couple of example problems. There is a homework assignment up there. Answers are posted for that homework assignment. Today, we'll move on to section 7.2 on impulse, and we'll talk about how it's related to section 7.1 from yesterday. There is also a homework assignment posted there. Answers are posted for that as well. Tomorrow, we will do some text polling that relates to the concepts that we talked about in 7.1 and 7.2. So we'll look at a couple of ideas there and make sure that we understand the concepts that are going on, how they're related, etc., etc. Then, on Thursday and Friday, I'll give you 2 days in class to work on your lab that goes along with this section of this unit. So impulse momentum lab, we'll probably gather data on Thursday, and then on Friday you'll have time in class to work on calculations, analysis questions, etc., etc. You also, like for the data collection, it's a LabQuest lab, so we use a LabQuest. You also will be using 2 sensors simultaneously, force and motion. Right? Whoa, I know it's a lot going on. So that's our lab on Thursday, and then on Monday of next week, you will have your quiz over the first part of this unit. It is an open-no quiz. Might be a little bit bigger than maybe trending more towards the 20-point range as opposed to the 10-point range. And then also your lab is due. On Tuesday, we will have time in class to review for semester exam stuff. I think I mentioned to you guys before, but in case I haven't, first I've given you all your test specs. You can use those to study. I gave you a review sheet before you went on break in December. Also, as far as reviewing for the exam goes, you will be allowed to use a note sheet on the exam. Not just a note card, but I'll give you a one full 8.5 by 11 sheet, front and back, make the margins 1/4 of an inch, use size 4 fonts, whatever. Just do whatever you need to do. So, yeah. But anyway, whatever works for you. So, and then I believe you guys are taking this exam on Thursday. Is that correct? Yeah, Thursday at 9:40. So you can see a.m. See how that looks. All the lighting angles will be different. Yeah, it's gonna be. All right, good there. It's right there. You're the second one on Thursday. Okay, yesterday we introduced this idea of momentum. And we talked about that momentum depends on 2 factors, yes? What are the 2 factors that momentum depends on? Mass and velocity. And it's just to calculate the momentum, it's just a simple product between the mass and the velocity. So P is equal to M times V. We use P to represent momentum, right? I know P doesn't show up anywhere in momentum, but that's the letter that we use to represent it, okay? And then from the unit standpoint, right, nothing special as far as the unit goes, just mashing together the 2 units that go along with mass and velocity. And we spent a good amount of time talking about how the fact that momentum depends on velocity means that momentum is also a vector quantity, that it has direction associated with it. And we use beanbag bear and red bouncy ball to illustrate that, and looked at the change in the momentum, especially for a bouncing ball or a bouncing object, an object that goes back to the direction that it was originally traveling from, and that change in momentum is a very large change in momentum because of the change in direction that's involved. And then at the end of class yesterday, we talked about that momentum being a vector means that we have to take care of those kind of things when we are calculating total momentums, which will be important when we get later in this chapter, section 7.3 and 7.4. We'll talk about conservation when we have to look up the total amount of momentum, but because momentum is a vector, we have to take that into account. And we did, right at the end, we did the duck, duck, goose problem, right? We talked about the signs and things like that, but we talked about that, the fact that the goose is going one way and the two ducks are going the other way. That means one of them is going to be positive, the other two are going to be negative, and we have to take care of that. Okay? Good there? Before we move on to section 7.2, just to sort of illustrate that idea, are you kidding me? Oh, no. There we go. There we go. To illustrate that idea, here is question number 6. Can't remember what page it's from, but it's question 6 from your book. You don't have this on your sheet. I just wanted to use it to illustrate an idea that's going to come back to us a little bit more. So you don't necessarily have to write this down, just kind of pay attention, and then we'll go with it. So it says, no, it's not on your sheet, yeah. So the numbers are actually very similar, and that's going to actually work out for us, but in this one, actually, this problem specifically isn't there. So it says, a 1,200 kilogram car moves due north with a speed of 15 meters per second. An identical car moves due east with the same speed. And it says, what are the direction and magnitude of the system's total momentum? So system's total momentum means sigma p, right? Sigma being the summation function, right? And we talked about that when we do the sum of that, mathematically, that's what we're doing. Okay? However, like I said, we spent a good amount of time yesterday talking about the idea that momentum is a vector quantity. So technically, we're not doing this. We're doing this. Right? Does that make sense? Okay. So, we have two cars. Car 1 is traveling in this direction. And if we want to find the sum of the momentum, we have to find the momentum of each individual car. So 1,200 kilogram car, speed of 15 meters per second. To find its momentum, we would just do what? Multiply those together, and I think if I remember correctly, it's to be 18,000. It also says we have an identical car moving with the same speed, but traveling due east. So if it has the same mass and the same velocity, it has the same momentum. We're trying to find the total momentum. We have to add those together, but we run into a problem in this one, right? What are we seeing about these two vectors? Different directions, okay? What do we do here? How do we add these vectors? Make the triangle, right? We have to line them up so that one, goodness gracious, this is going to turn out bad. We have to line them up so that one ends where the next one begins, or vice versa. Oh, goodness. That looks good right there. So we have to line them up so that the next one starts where the first one ends, right? And then make the triangle, right? We have a fancy name for making the triangle. What do we call it? What? Ooh, look at that. Did you just pull that out? Like, man. So. We have to find the resultant vector. Okay, just a little FYI. You're probably going to see this again next Thursday, just so you know. Find the resultant vector, right? And the resultant vector represents the vector sum of those two. Okay? Now, they made it a little bit easier for us because the fact that these have the exact same momentum means what about this angle? If the two sides of this triangle, or the two sides of the right triangle are the same, what kind of a triangle is it? It's a 45, 45, 90, right? So that means that this has to be 45 degrees, and then we would find the purple just by doing what? What would we do to find the purple? we would use, well, we could do that, or we could use what? Pythagorean theorem, right? Find that. Okay. Did you run it through, or? Well, I mean, it should be pretty big because you're squaring 18,000, right? So square 18,000 squared plus 18,000 squared, square root of that. Something big. So. It's got to be bigger than 2,500. Is it 25,000? Yeah.
It's got to be 300.
All right, good there? Okay, let's get on to the business of today, and let's talk about impulse. So, there's a little story up here that summarizes the idea of impulse and what it's all about. So it says, next time you push a shopping cart at the grocery store, notice how long it takes to accelerate it from rest to walking speed. So, I know. Well, let's talk about it this way. Let's say you're there with a small kid, a little brother, a cousin, some kid you're babysitting, whatever it is, right? And they want to push the cart. Okay? They're going to push the cart, and it's going to take them a while to get it up to like a normal everyday person speed, right? Because they can't really push as hard. But if you take that cart, you can get it going fast much more quickly because you can apply a greater force. Eventually, you both could end up getting the cart moving the same speed. The little kid would just take longer to do it. So when we talk about impulse, we're talking about two factors, right? How hard you push, but then also how long are you going to push that object? Okay? So impulse depends on two factors. A force acting for a time produces an impulse. So the impulse of an object is equal to the force multiplied by the time interval. I is equal to F times delta T. Okay? Now, Luke, you kind of mentioned this before, right? Force is newtons. Time is seconds. So the unit for impulse is N times S, newtons times seconds. But, maybe you recall, maybe you don't, but newtons is a combination of base units, kilograms times meters over seconds squared. If we then multiply that by seconds for the time, right? This cancels, one of those cancels, and we're left with kilograms times meters over seconds, which is the same unit that we introduced for momentum yesterday. Why? Because the impulse, okay, let's go this way. Here is a situation similar to the red bouncy ball that we talked about yesterday, right? This baseball is originally traveling towards the left, now it's traveling towards the right, before it gets hit, after it gets hit. This is a change in momentum, and a relatively large change in momentum, because of the whole change in direction thing. Impulse changes an object's momentum. The force that is applied over a certain amount of time causes the momentum of the object to change. Could increase, could decrease, could go exactly in the other direction. But there is a change in momentum because of impulse. The fact that when we calculate the impulse, it gives us the same unit as it did for momentum means that impulse changes momentum by the same amount. These ideas come together to give us the momentum impulse theorem. that says that the impulse that acts on an object is equal to the change in the object's momentum. The key word in this sentence here being the change in the object's momentum. Impulse doesn't equal momentum. Impulse equals the change in the momentum. Okay? Good with that so far? This equation right here is a pretty simplistic mathematical representation of the momentum impulse theorem. But it's not the most useful representation when we're trying to figure out things and analyze situations. So let's expand this a little bit. First, we just learned that impulse depends on two factors. Do we remember the two factors that impulse depends on? Force and time. So we can change the left-hand side of this equation to look like this. The right-hand side being delta P, right, the change in the momentum. We know that when we calculate the change in anything, P final minus P initial, right? But we learned yesterday that the momentum of an object, whether it's the final momentum or the initial momentum, depends on two factors of its own, right? What are those two factors? Mass and velocity. So, we expand it out and now it looks like this. This version of the impulse-momentum equation, or momentum-impulse theorem, right? It's exactly the same as this, just a more detailed version. But these things, like force, time, mass, and velocity, a lot of times are easier to measure than the impulse and the change in momentum. If we measure the force, the time, the mass, and the velocity, we'll be able to verify that. Okay? Good there? All right. Before we go on and see how this works in an equation, let me show you this. Does that look familiar? Hopefully. Okay. You're going to need to know that next Thursday, by the way. Okay. So, Newton's second law. But we talked about the idea that force causes acceleration and they're direct related and all that kind of stuff. Okay? And all those things are true. But one thing that we didn't talk about is that whole time factor. Okay? You can apply a very large force to something, and it can cause a very large acceleration. But if you only apply that force for a very short time, the overall change in its motion isn't going to be that great. Does that make sense? Right? If I have something like this, right, and I apply a large force, but only for a very short time, not all that much happened. Okay? But Newton even knew when he was developing this concept that we can take this equation and break it down and make it more detailed. For example, does that make sense? That's how we define acceleration, right? Change in velocity over change in time. If I rearrange this equation, I get it to look like this. Notice any similarities between those two? They're basically the same equation, right? We factored out m from the left-hand side of this equation, right? But it's the same thing. Impulse momentum theorem is basically Newton's second law, just a little bit more detailed. Okay? Good there? All right. Let's take a look at the front of page 2, or like page 3 of your packet. Example 7.6, lending a hand. So it says, 3 friends push a stalled car and its driver to a nearby service station. Assume the car rolls without friction on a smooth and level road. If the car is at rest initially and the 3 students give a combined push of 305 newtons, what is the momentum of the car and the driver after 12 seconds? So we start off with what this question is asking us for, right? First, what is the momentum? And the fact that after shows up means which momentum do we want to solve for? Whatever after shows up in our description, right, that's telling us that we're looking for the final something. Okay? What else did they give us to work with? Okay? They definitely straight up gave us a time of 12 seconds. Okay? Force of 305 newtons, okay? They also gave us a initial velocity, that initial velocity being, right? Now, that's okay, but we can also sort of make an assumption as well that if the initial velocity of the car is 0, what else has to be true? If we think back to like yesterday, if the initial velocity is 0, what else has to be true? The initial momentum has to be 0 as well. Okay. Good there? We just learned that the impulse momentum theorem tells us that the impulse that acts on an object is equal to the change in its momentum. But we learned that these also have a more expanded form that maybe helps us analyze things in specific situations a little better. Okay? We just talked about that the initial momentum of this object was what? 0. We know the force, we know the time, so we can figure out what P final would have been, or is. So go ahead and figure that out. I think you end up with 3660, okay? Units, you multiplied force and time, so you get newtons times seconds. But we talked about earlier, right, that if you have newtons times seconds, it simplifies to the unit for momentum. So you can either keep it that way, or you can write it as kilograms times meters over, or kilograms times meters over seconds. I don't know how well that's going to catch on, but you know. Right? Part B. What is the car's velocity after 12 seconds? If it's asking you for velocity after 12 seconds, what's it asking you for? All right. In the previous problem, we calculated what? The final momentum, and in part B, they gave you the mass. If you know the momentum and the mass, you can figure out the velocity, right? Because we know that P is equal to M times V, and more specifically, P final is equal to M times V final. So to get V final, you're just going to take what? You're going to take momentum and do what to it? Divide it by the mass. And if I'm not mistaken, the 2.67? Is that what it ends up being? All right, good there? Okay. On the calendar for tonight, there is a homework assignment that relates to Impulse. Answers are posted for that homework assignment. Tomorrow we will get into some concepts. We'll do some text polling, so if you don't bring your phone for any whatever reason, bring it tomorrow so you can participate. Okay? All right.